The core paradox of autonomous software agents is simple. We want them to write code, but eventually we have to run it. Large language models are highly capable, but inherently unpredictable. Handing a model direct, unconstrained access to a host operating system means exposing your infrastructure to unintended commands, infinite resource loops, or outright malicious scripts. To solve this, system architects enforce a strict physical decoupling. The environment where the AI formulates its logic must be completely severed from the environment where that logic is carried out. Before a single line of generated code executes, the system must establish a verified isolation boundary between the model and the host. OpenHands is an open-source, cloud-native platform explicitly built around this decoupled architecture. This maps the 5 core OpenHands primitives: file system, code execution, sandbox, memory, and context management. They link together into a continuous cycle known as the agent loop. Let's trace the exact lifecycle of a single user turn as it navigates this entire event loop. The request starts at the system's entry point, hitting the central FastAPI application server defined in app.py. From there, it moves to the V1 router. This acts as the routing hub, aggregating endpoints for events, sandboxes, and platform settings. Standard web architecture usually relies on linear HTTP request-response cycles. Autonomous agents, however, require continuous communication to handle tasks that take unpredictable amounts of time to complete. To support this, OpenHands replaces the standard HTTP call with a dedicated set of bidirectional WebSocket pipelines. This setup lets the application stream user interactions and agent responses back and forth in real time. The main application thread never blocks while waiting for the agent to finish a long-running process. This WebSocket event stream operates as the central nervous system of the architecture, actively maintaining the agent's context over extended interactions. The user request transitions from the event stream and lands in the AgentController for evaluation. Before the model can generate a valid action plan, it first assesses its current memory state and queries the specific tools it has available. The system pulls in specialized capabilities through the skills router, which loads dedicated microagents to handle specific programmatic tasks. Simultaneously, the controller pings the FastMCP proxy, retrieving a package of external tool schemas. Using a proxy to mount these tools keeps the reasoning logic clean. If you hard-coded every API integration directly into the agent, the core codebase would quickly become unmaintainable. This modular context layer lets engineers scale the tools the agent can access without bloating the underlying FastAPI application. Now the AgentController has its context and formulates a plan, an action payload that requires executing an arbitrary Python script. At this exact moment, the platform's core security directive takes over. The app server will never execute this code locally. The architecture relies on the isolation seam, a physical boundary severing the reasoning server from the execution runtime. The payload hits the sandbox router, where authentication middleware verifies permissions. Once cleared, the sandbox service spins up an isolated Docker container. Encapsulating execution into this strictly managed container guarantees that any faulty syntax or destructive commands are completely quarantined from the host system. Inside the container, the untrusted code runs against an isolated disposable file system. The resulting standard output and error tracebacks are captured and transformed into an observation payload. This payload reverses direction, safely crossing the isolation seam. The data flows back up the asynchronous WebSocket channels directly to the AgentController. Receiving this observation updates the agent's internal memory state. The model processes the result, evaluating whether the task succeeded or if it needs to write a new script to fix an error. A true autonomous workflow is a continuous, iterative cycle of action and observation, repeating until the software problem is solved. When we zoom out, we see the entire OpenHands architecture functioning as a high-speed, autonomous loop. This event-driven cycle allows the agent to iteratively write code, test it in the container, read the resulting error logs, and correct its own mistakes entirely without human intervention. The efficiency and safety of this self-correcting process rely entirely on the rigid enforcement of that execution boundary. Separating the reasoning engine from the execution runtime is the architectural pattern that makes enterprise-grade AI deployment viable. The landscape of software development is shifting heavily towards autonomous agents. Reliability in these agents is a product of the rigorous systems engineering surrounding the language model. We see that through the 3 pillars demonstrated today: injecting modular context via FastMCP, managing state asynchronously through WebSockets, and enforcing hard isolation boundaries using container orchestration. OpenHands provides a blueprint for this interaction, demonstrating how to safely contain, contextualize, and loop autonomous AI behaviors.